Yes, please.
A very good evening and warm welcome to everyone present here. Today, we all have gathered here to witness the seventh lecture of our Centenary Lecture series. Today, the lecture will be delivered by Dr. Barun Chakrabarti, sir, on the topic of asset management in digital age, enriching expertise with smart solution. As the chair of this session today, we have Professor Parthapratim De, Professor, Department of Mechanical Engineering, IIST Shibpur. Now I would request Sir to take over the charges as the chair. Sir, please.
Very good evening to our speaker, Dr. Varun Chakravurti, our respected alumni, faculty members, dear students, and ladies and gentlemen, all present on this online event. This is already the seventh centenary lecture. So already we have six centenary lecture in which we have already big names like Professor Amitav Ghosh, Professor Achyut Ghosh, Professor Ashok Mollik, Professor Kamal Sarkar, Dr. Purandar Bhattacharya, Dr. Gautam Vishwas, and today we have Dr. Varun Chakrabarti from L&T. Let me introduce Dr. Chakrabarti. He is our alumnus. To go through his CV, Dr. Barun Chakrabarti is currently working as the head of the Center of Technical Excellence for Asset Management Business of Larsen and Toubro Hydrocarbon Engineering. During his more than 24 years of experience with L&T, he has held several key positions such as subject matter expert for asset integrity solution and head of the R&D center. His areas of expertise include asset integrity management, smart asset management, machinery diagnostics, tribology, and advanced engineering analysis. He has over 34 years of professional experience covering hydrocarbon, power, cement, mineral, and industrial machinery sectors. Prior to joining L&T in 1998, Dr. Chakraborty worked in the R&D Center of NTPC, New Delhi from 1990 to 1998 and Gaskin Williams, Kolkata, 1986 to 1988, 2 years. Dr. Chakraborty obtained his bachelor's in mechanical engineering degree from Bengal Engineering College. It was under Calcutta University in 1986, and he did his MTech in industrial tribology from IIT Madras in 1990. He completed his PhD from IIT Delhi in 1996 in the area of diagnostic expert system. He has several academic distinctions to his credit, such as National Merit Scholarship and the Governor's Medal for the State of West Bengal and University Merit Scholarship. Dr. Chakrabarti has a very brilliant academic record, and it shows in MTech he was a 10-pointer at IIT Madras. Dr. Chakraborty is a live member and current vice president of the Tribology Society of India. He has served as a member of the editorial board of Indian Journal of Tribology. He is also a live member of Indian Institute of Plant Engineers and a member of the Society of Tribologists and Lubrication Engineers, USA. He has close link with academia and has served as the accredited external examiner at IIT Mumbai and Mumbai University. He has been a member of the Board of Studies in Management at Mukesh Patel School of Technology, Management and Engineering, Mumbai, and Sardar Patel of College of Engineering, Mumbai. He also served an external expert of the peer review committee of IIT Roorkee. He has been a member of the expert panel of the National Board of Accreditation (NBA) for engineering institutions. Dr. Chakrabarti has been associated with several major initiatives of industry association such as FICCI and CII related to industry-academia collaboration, skill development, technology and innovation management. He has many technical publications in reputed journals and conferences to his credit. He frequently delivers talks and invited lectures at industry events. So now I cordially invite Dr. Varun Chakravurti to start his speech for today's centenary lecture.
Yeah, thank you very much for the introduction and a very good evening to all of you. It's my proud privilege to be a speaker in this gathering and getting the opportunity to share some of my learnings in the long stint that I have had in the industry. Let me try to share my uh, screen so that the presentation is visible. Please confirm when the screen is visible.
Yes, sir, the screen is visible.
Okay.
Yes, slides full.
This evening, I would like to talk about asset management. I am from the industry, and the industry basically operates with a set of assets, very diverse kind of assets. And as we have shifted from the traditional days of running an industry and the industrial assets to the current digital age, what has got transformed in the industry and how we are looking at this transformation, how we are managing the change, and how people are coping with this. That is the topic of this evening. And basically, I'll try to establish a synergy between the expertise that we humans have and the smartness that the digital solutions provide. Are they conflicting to each other, or they can really be supplementing each other? So that is the topic I'll be speaking on. Basically, there are three themes. One is the asset management. What do we mean by asset management in the industry? And with a specific reference to one class of asset management area, that is machinery diagnostics, diagnosing faults in running machines in the industry. I'll share some examples just to show how we humans handle such challenges in the industry. When a machine is giving a problem, what would the expert do, what would the operator do, and what the solution would be like if it is handled by the humans, as we have been doing traditionally. And the next section, the digital impact, I would like to show the same kind of problems, how it would be handled by the so-called AI tools or the digital solutions, and where the conflict is, where the complementary nature is. And we'll try to set some kind of a balance between the traditional versus the smart solutions. Today's reality is, and I think all of us are exposed to this, myself included, we are constantly bombarded by a lot of jargons. As you can see on the screen, we understand some of it, we do not understand most of it. But one thing that we know for sure is that they're really impacting our lives, both professionally and socially, and they're going to impact and transfer our lives the way we would be living it in future. So one offshoot of this is, of course, on the industrial sector, where we have seen the advent of IIoT and how it is transforming the way businesses are run. Machineries are designed, manufactured, engineered, and operated in the industry, and how this could be helping us in meeting many of the challenges that we may face in the industry. Coming to the basics of asset management, let us try to understand why this is important for us. What do we do under asset management? Who are the people or the stakeholders here? And why it is so important for us? Basically, the industry would need to do managing the management of their assets primarily because of the regulatory requirements that you have to comply with certain regulations and laws as you do your business. You, of course, have to uphold the safety performance requirements. you need to afford the performance of your aged plants as the machinery become old. And the other thing which is very critical today in the industry is, can you avoid or defer your capex decisions? Try to avoid putting a lot of money when the industry condition is so uncertain and you do not have clarity about the future. You can only do that or take the decision once you know precisely what is the health of your current set of assets in the plant. And also at the enterprise level, where a very large conglomerate, for example, of course will do in it. But suppose a company of the size of L&T having multiple diverse businesses have to take a balancing decision with respect to their capex deployment and the performance enhancement of their business. What kind of information they should have, and precise information about the health of the assets, how long they can operate, with what efficiency they can operate. These are some of the considerations that come under asset management. So who are the stakeholders? We have, of course, the owner and operators, the industrialists who own these assets. We have the technology licensors who provide the know-how for building these plants. We have the consultants or the domain experts who contribute their expertise in helping the owners run the plant. We have a lot of service agencies who perform the NDT checks, the cathodic protection studies, the refractory refurbishment services, the operation and maintenance services. And we have the OEM of the equipment and systems who actually design and manufacture these plant and machinery and install them in the industry. And also today we have a lot of software solution providers who are trying to build software which can help the owners run their business profitably. So this is a very close knit ecosystem where multiple agencies are playing, and they are complementing each other's effort to make the business grow and develop, and also make it profitable and mutually beneficial for each one of them. So the key expectations from managing assets is that if you talk about assessing the health of running machinery, we want to transform from a reactive mode, which we have been doing traditionally, to a more proactive approach where we can actually predict and diagnose what is going wrong with the machine, what can go wrong in future, and how to do the remedial measure. And basically, we want to replace the traditional NDT checks, the non-destructive testing that we do on the machines, the DPT, the MPT, the ultrasonic testing, to a more holistic health assessment program for the machines. And can we extend the life of the machines once we know at what stage of life, useful life they are in? And how to implement the various digital solutions, some of which I showed in the opening slide, the IoT concept, the digital twin concept, the remote dashboard concept for the management. And to have a complete solution package rather than taking piecemeal solutions for a multitude of agencies, can you have a complete solution package on a digital platform which can really help the owner operators to derive maximum benefit from their assets? Some of these thoughts have now been standardized and codified in terms of a code, that is ISO 55000 series of standards. So you can say that the asset management approach, which developed in different channels and different ways across the world in different countries to a different extent, have now been refined, consolidated, and compiled into a standard, which is ISO 55000, which basically govern the way we do asset management in industry today. What could be the asset management solutions when you are managing an industry that has, for example, few hundred rotating machinery, a few thousand static equipment, kilometers of pipeline or piping, and a lot of other things built into it? What kind of solutions do you need to run this without any damage or catastrophic failures or accidents, and at the same time deliver the profitability that you are looking for? You need to understand about the integrity of these assets, right? Are they in a fit position to run and deliver what they are supposed to deliver? Then the performance improvement piece, are they delivering at the optimum level, or there is still something left that you can extract? There are programs in the industry where you shut down the plant for a few days or weeks or months and then refurbish the machinery, overhaul them, and put them back in as new conditions, so to say, so that the performance can be improved. And you have a lot of programs like modification, upgrade, debottlenecking, where you again try to basically enhance the performance of these assets. And of course, you have the routine operation management and the maintenance management just to keep the machines running and to derive the output that they're supposed to give. So as you can see, it is not one solution or two solutions. It is a complete set of solutions that you need to have at your disposal to run and basically operate your industry in the best possible way. So this is a traditional definition drawing from the concept presented by ISO 55000. There are three elements, basically the assets, the integrity of the assets, and how do you manage. Assets are, of course, all the physical assets. Of course, in financial term also, people call it asset. For example, you have asset management company in the insurance, in the banking and other things. But here we are talking about physical assets in the operating industry that include the plant and machinery, the offshore assets for oil and gas industry, the onshore pipeline and the pipings, the civil infrastructure, all the buildings, bridges, flyovers, highways that you see, most of which we also build through L&T. Transportation assets, the power sector assets, telecommunication assets. There is no end to this list. Everything that you see around, which operates and provides us the environment that we live in and the businesses that we are engaged in, these are all assets. Now, coming to the integrity aspects, integrity means that the asset should perform safely and deliver the intended output or the function in the prescribed conditions or environment over a specific period of time. This is very important to understand because the asset life cycle is not infinite. Any plant or machinery that you install in the industry today will have a definite life over which it can operate and deliver the output for which it is designed. So there are three parameters basically. One is the safety compliance, that is very important. Then the intended function. It is not that everything you can do with a given asset. It will only deliver as per the way it has been designed and engineered. And in the environment, suppose you are supposed to run something in a sub-zero temperature, you install the same machine in a desert condition. Will it perform in the same way? And of course, as I mentioned, the definite life cycle, the specific period of time. And managing the integrity of assets is basically you take proactive measures and you plan your actions to see that the integrity of these assets is not compromised. And also, if you see that something is going wrong, you take prompt remedial measures so that it cannot further deteriorate and lead to some catastrophic failure. So what are the tools and techniques we have at our disposal to achieve these kind of goals? One is at the design and engineering of the plant, at the phase of design and engineering, when you are conceptualizing how the plant look like, what kind of machines it should have, what kind of specifications those machines should have. And you have certain techniques today, of course, we do simulation to a large extent in designing plants and machinery, both from the process side, from the mechanical side, and the thermal fluid side. You have a lot of design techniques and software tools available. You have the design verification. Earlier days, people used to run, even today in some industries, you have pilot plants for trial runs of new designs. But mostly these are being done through simulation today. Scale up studies, prototype testing, pilot plant trials, experimental stress analysis before you can perfect the design of the machines. And then, of course, you do the reliability assessment. Will it have 95% reliability? Will it have 99.9% reliability? You design that in the engineering phase so that you get the optimum output when it is put into practice. And one major degradation mechanism that we face in industry, at least in my industry, that is hydrocarbon, is the corrosion risk. And we do a lot of simulations to understand that risk, the corrosion rates, what kind of protection you should build into the design to avoid corrosion and things like that. Now we have put the machines in the plant and it has entered the operating phase. What kind of tools or techniques we have at our disposal to ensure integrity of assets? One is the periodic monitoring that we do, vibration measurement, noise measurement. We have debris analysis in the fluids, particularly the lube oils, thermography, which is the thermal imaging of the hot surfaces, and monitoring of the process parameters. As I mentioned earlier, you have a lot of non-destructive testing at your disposal. You can do these tests without disturbing the component and try to understand at what state of health it is in. Today, with the involvement of a lot of digital tools, we have the capability of remote monitoring of your assets and doing some element of diagnostics. We have in-service inspections, particularly for the pipelines, where in the running condition, you can put the pigging instrument in the pipeline and exactly see where it is cracking, where it is getting deformed, what extent of corrosion it is seeing. We do a lot of inspections when plants are shut down and gather a lot of data about the health of assets. We do the reliability centered maintenance program in the operating plants to see how the reliability is going down with the aging of the equipment. We do some of the specialized techniques. Of course, I won't have the opportunity of explaining any of these today. Just to let you know, the fitness of service or FFS, the residual life of equipment, which is RLA, and the root cause analysis technique, which is RCA. These are some of the techniques we frequently use in industry to understand the health of machinery and how we can extend the useful life. Now, there is a concept of asset life cycle. Though traditionally, when you talk about asset management, people only talk about the operating phase of the plant. For example, a plant that has been installed today and it will probably run for 20 years, 25 years. You focus only on that operating and maintaining phase of the plant. But the reality is that if you really want to do asset management in a holistic manner, you have to start from the design and conceptualization of the plant itself. So that is how I have shown here. Your asset management actions actually start from the design phase, going through the engineering, manufacturing, assembly, installation, commissioning of the plant, performance trials. Then it gets into the conventional O&M phase, as we call it, operating and maintaining phase. And towards the end of the life, of course, you shut down the asset and then you decommission it, and that's the end of life. So the key to successful asset management would be this cradle to grave approach, where you start from the conceptualization of a plant and it ends with the decommissioning of the plant. And through the entire life cycle, you adopt the tools and techniques just discussed to do the asset management in the best possible way. This plot may be familiar to many of you. This is popularly known as the bathtub curve because of the shape of the blue line that you see. It is like a bathtub. It actually shows the failure rate of assets with respect to time. And it has three independent segments. I'll try to briefly explain. When you install a new asset, it has a high probability of failure because of inbuilt defects, workmanship, assembly, material selection, whatever it is. And this is known as the infant mortality phase. It can suddenly fail, very new piece of equipment. So as you see, it is very high at the beginning, the red line at the left hand side, and as time goes, the operation stabilizes and the risk of this kind of failure minimizes. The other type of the failure is what is shown in light brown, which is a wear out failure. As the asset becomes old and the aging sets in, it will have its life basically restricted, its operating regime getting restricted because of the aging, and a lot of problems, age related problems will come, just as we humans age with time. So that is the brown line that you see towards the right. It is going up, means the failure rate increases because of the aging of the assets. And then you have the most interesting piece of information about the failure, that is the constant or the probabilistic failure rate, which is a flat line across the life cycle of the asset. You do not know when it will fail because it is failing because of random causes. Now, if you superimpose these three lines, the infant mortality failure rate, the wear out failure rate, and the constant or the probabilistic failure rate, you get the actual observed failure rate across the industry, which is the blue line on top. So initially you have a high probability of failure. As it matures, the asset matures and stabilizes in its operation, it becomes flatter, and then it becomes older and older, and the failure rate again increases. So this is the basic philosophy of how you want to do management of your assets as it grows older. And to do that, we have several philosophies of maintaining the assets, which have evolved over time. I mean, what you see on this slide is probably an evolution over a century of industrial development. Initially, people would only do breakdown maintenance because we didn't have any tools and techniques at our disposal. So you just attend to the equipment when it fails and try to do something, or you replace it. We still do that for systems which are non-critical and where you have redundancies built in. You have other alternatives which can start operating in place of the failed equipment. Then comes the time scheduled maintenance, which is the most prevalent even today, though it is not the most efficient way of doing maintenance. But we do today for very critical assets in the process industries, turbo machinery, power plant equipment, oil and gas production equipment, where you can't afford to have failures. So every say 2 years or 3 years, you stop your plant, you do a complete overhauling, and you rectify the faults that are developing and put back the plant in operation. But this is not really cost effective. You do a lot of unnecessary maintenance where it would not be called for. So that is why people gradually switch to condition based maintenance, where you do the maintenance that is actually called for by the prevalent condition of the asset. You try to do some health assessment on the asset, do a lot of assessment in terms of vibration, stress analysis, then microstructural analysis for the material, and try to see at what condition it is, what kind of maintenance it may require today or couple of years down the line. And the latest that we have today, which is the state of art, I should say, is the diagnostic or proactive or prescriptive maintenance. People use different terms, but it all means the same thing. You basically see the condition today as accurately as possible. Try to diagnose what can go wrong in future, and accordingly, you basically coin your maintenance philosophy. How we'll be doing maintenance of the asset. With this knowledge of basic asset management philosophy and the approaches, let us now see how we are doing this in real life industry. Okay, I'll only illustrate the common machines machine components that we are aware of, for example gears and bearings and stuff like that. And though these are part of the whole plant, they are not the plant by themselves, but their failure is very critical for the running of the actual pump or the turbine or the compressors. Okay, now, I'll start with gears. Gears are very popular machine tools. Right from our engineering days, we have learned how to design gears, how to manufacture them, what kind of problems you see in gears, how to troubleshoot gears. So that is how, based on that collective knowledge, some kind of philosophy has developed in troubleshooting of gears, which you see in the table. For example, if you are doing vibration analysis on a gearbox and you see certain vibration pattern, you see the spectrum taken from the vibration measuring instrument or the vibration analyzer, and try to diagnose what is going wrong inside the gearbox without even opening it or stopping the plant. So if you have certain kind of faults which are shown on the left, if you look at the frequency spectrum, you see mostly it is gear mesh frequency or multiples of gear mesh frequency, or the natural frequency of the gear or the pinion, or various combination of these. And what could you infer from this information? Based on that, you can say, okay, if you are saying gear mesh frequency, this could be the problem. If you are seeing a lot of sidebands, this could be the additional problems. You will see, particularly because gear is a kind of evolving or a dynamic situation when it meshes with the pinion. You always see a modulation effect, and you have vibration signature analysis techniques that do the demodulation of this complex signature and bring out the frequencies that are of interest to us, through which we actually identify the faults which are listed on the left. Now, there are some mathematical basis for this. As you know, in gear and pinion, we have a very periodic kind of engagement through the machine. And in terms of the gear tooth, pinion tooth, running speed, you can have various combinations of probable frequencies that you may see in the spectrum. Okay, and you see some of the spectrum samples on the right hand side. These are very complex. It is if you are not into this area, it is very difficult to make a head or tail out of these kind of plots. But if you know the right information and you are utilizing the right technique of analyzing the signal from the gearbox, you should be in a position to diagnose the fault or the problem that is going on inside. And the frequency spectrum analysis techniques, some of these I have listed here, which we are typically using in the vibration analyzer when we are analyzing gearboxes. They throw up the fault signals, and through that you diagnose the fault, and once you know the fault, you also recommend the corrective measure for the gearbox. These are some of the actual plots. As you see, some of the faults are mentioned here. Of course, I will not go line by line, just to tell you that the dominant frequency in a gearbox spectrum will be the gear mesh frequencies, and depending on the severity of the problem, you will see multiple sidebands, very large amplitude lines vertically, and you will sometimes see even natural frequencies of the gears and pinions if they are having cracks. These are some of the information that the expert should be in a position to extract from this. It should not be too difficult for him. Now, when we go to the second part of my talk and we talk about digital solutions, I'll try to explain how this kind of a diagnosis, which is being done by the human expert based on his experience, would be done by the AI tool, for example. Is it possible at all? Can the AI tool do a better job, or can it not do this kind of diagnosis at all? That would be interesting to discuss. Okay, some similar kind of spectrum. Here you see some of the other classes of faults. You see a lot of subharmonic lines on the left hand side, which shows a lot of incipient damage, which are not very prominent yet in the machine, but they may cause you trouble in the future. These are some of the things that I can read out of this, but probably if you really get down into the mathematics and extract the frequency and try to correlate, you will also arrive at the same kind of diagnosis. Coming to the rolling element bearings, by the way, dynamics wise, they are very similar to gear mesh. You here also you have a set of contacts which are periodically engaging and disengaging, and you have multiple components in a rolling element bearings. As you know, you have the rolling elements, you have the inner race, you have the outer race, you have the cage, and all sorts of combination of faults can occur. And rolling element bearings are very sensitive devices. If you mishandle them, half their operating life will go. So, and of course, on top of that, you have a lot of materials related damage that are possible. For example, spalling, wear, fretting, corrosion, improper installation, improper mounting, inadequate lubrication, risk of electrical discharge, particularly rolling element bearings installed on motors and generators. You can have load overruns, you have overspeeding, you have excessive point load applied on a bearing. There are many things which are possible, and we do have some understanding today. If you see the body of literature that deal with the fault diagnosis of rolling element bearing, we are comfortably placed in terms of if you have the right kind of tools at your disposal, you should be in a position to, with some sort of certainty, predict what is going wrong in a bearing installation. And then again, just like in the case of gear analysis, we have the frequency analysis tools at our disposal, where you analyze the signal, raw signal coming from the bearing installation, extract the frequencies, and then try to diagnose the faults that would be present there. And again, like gears, you have a set of characteristic frequencies depending on the bearing design and its operating speed. Whether the fault is occurring on the inner race or the outer race or on the ball or the roller or in the cage, you get a very typical characteristic frequency in the spectrum. If you know the bearing design data, you know which frequencies to expect. If you have those frequencies present in the spectrum, you know what the problem is. Okay. And you see some of the time domain signatures on the right as the bearing runs, how the defect gets excited, the defect area gets excited within the bearing. You will get these spikes in the time domain signal. You can convert them into frequency spectrum. You will see the single lines at those locations of the frequency. And once you match with the frequencies which are shown by the wall pass frequency or the inner race or outer race frequencies, you know that is the damage. The crack is there in the inner race, the damage is there in the roller, or the deformation is there in the outer race, and things like that. So once you know that beforehand how severe the problem is, you may recommend the operator to run it for some more time till the next plant shutdown, or if it is too serious or severe damage, you recommend replacement of the bearing at the same instant. These are just some examples of how you read the spectrum, how we experts would be reading the spectrum to diagnose where the damage is. For example, very characteristical, if you see the picture on the right, where the black line actually shows a spalled surface inside the bearing, every time it is coming in the load zone at the bottom of the bearing, you just see a spike in the time domain signal. And if you convert this to a frequency spectrum, you will see a solid line at that particular frequency pertaining to the frequency of the inner race damage, and you know there is a damage in the inner race without even opening or inspecting the bearing physically. So that is the kind of facility we have today. Coming to the journal bearings or fluid film bearings, there also we have a set of approaches to diagnose what is going on. Now it is comparatively difficult to handle compared to gears and rolling element bearings. In journal bearings, as you know, it is very difficult to open the bearing, and you cannot really replace the bearing. You do a lot of online monitoring through the proximity probe system to pick up the displacement signal from these bearings and try to analyze as much as you can through a set of plots or curves which are characteristic of different failures. I'll explain some of these. For example, the vibration analysis is basically done in terms of some plots like orbits, time-based plots, or frequencies plot for the frequency component. The amplitude and phase is basically read from the Bohler plots, and the position of the journal within the bearing space that basically tells you about the loading extent of the bearing, whether the bearing is unloaded or overloaded, if the shaft is eccentric within the bearing, if it is touching the bearing and damaging the surface. All these kind of things can be predicted depending on the plots that you have generated from the machine and the way you are studying those plots or interpreting those plots. The basis of monitoring today in journal bearing faults, install journal bearing. For example, if you have a steam turbine in a power plant or you have a compressor in a process plant, you install the proximity probes at 90 degrees, take out the displacement signals X and Y, merge them together on a software or on an oscilloscope, and you get the magnified image of the shaft movement within the bearing space, which we call as the orbit. Depending on the shape and size of the orbit, you can actually extract a wealth of information about the bearing damage. For example, okay, before that, let me show similar to the gears and the bearings. You have a very nice correlation between the vibration pattern and the different faults in the journal bearing. If you are able to spot these frequencies and monitor this kind of pattern of the frequencies over time, you can actually predict how the deterioration is happening in the bearing. There are various kind of damages or problems possible in a journal bearing. Some of these are listed here, and the characteristic frequencies. One thing that is very dangerous in a journal bearing is the subsynchronous vibration signature, which shows the instability in the bearing, which normally builds up and wrecks your machine. So you normally should not be expecting half frequency or subsynchronous frequency spectrum in your normal vibration signature from the journal bearing. Okay, I was talking about the orbits. So if you see different types of orbit shapes and sizes and the way they look like, where the key phasor dot is coming, how many of those dots are appearing, it tells a lot about what is going wrong in the installation in terms of the shaft, in terms of the bearing alignment with the shaft, in terms of the bearing's own health, whether it is having any damage, whether it is properly lubricated, if it is running at a very high speed approaching instability, or it is running underloaded. Basically, the orbit plot study tells you all this information, and based on that, you can take the corrective measure, or you can instruct the machine operator to run the machine in a particular way so that you don't run into further problem. I'll also briefly outline another technique that is very popular in the industry today, that is thermography, where you take a thermal image of the equipment or the component that you are studying and try to map the temperature distribution over the surface or the component and try to diagnose where the hot spots are. Typically, the rule is that you should not be seeing hot spots in a normally running healthy machine unless something is going wrong. Okay. For example, if you see on the left hand side, top and bottom, I have shown the thermography image taken from a bearing plumber block, rolling element bearing in a plumber block. On top of that, you see it is running almost white hot at one point, and that means it is extremely overheated. Probably it's a starved bearing. It is not having enough lubrication. It is about to seize. And the bottom, you see a flexible coupling in the middle. On the right hand side, there is a motor. On the left hand side, there is a gearbox. And the motor bearing on the drive side, as you can see, it is very white in color. That means it is getting extremely overheated, for which it is not designed. Again, you can understand something is going wrong in the motor bearing. You have to stop and inspect it. Maybe the lubrication is not correct. Maybe the bearing is having overload, or it is not properly fitted in the housing. On the right hand side, I have shown a lubrication failure situation in a gearbox. You see the pipes bringing in the lubricant flow into the bearing of the gearbox, but at the top as well as the gearbox covered face on the bottom, you see the yellow and white color that shows and also you see the temperatures being displayed here, because the thermographic camera had the facility to actually map the temperature and display the value. And looking at this and trending these values over time as you inspect the machine every week or every month, you can derive a lot of information about the health of the machine, the problems you are facing in the lubrication, and the corrective action that you should take to prevent any further damage. And this is something that is very uncharacteristic. Normally, we don't see. In fact, this is from my own experience in troubleshooting a very expensive damage in an expander bearing. And the only correlation we could find after months of study is one literature reference that you see on the top, which is basically from the bearing handbook, tribology handbook by Michael Neal. And the bottom picture that you see is actually taken by me from the industry when I was doing it at site. And you see how they match. And there is no further difference I could find but we successfully diagnosed the problem as the wear wool failure. Basically, we did the material testing of the failed bearing and actually came up with the kind of diagnosis which Neil had suggested in his handbook. And that is how the problem was solved, and it was found to be a materials problem, high chromium content in the bearing liner, and actually the OEM was obliged to supply the replacement bearing free of cost. Now, this is the kind of once in a lifetime kind of problem that you will find, where it is very difficult to know what. Luckily, in this case, we could establish the cause and we could get the compensation from the supplier. But we may not be so lucky every time, and some of these actually go undiagnosed, and we never knew what actually had failed and how it failed. That is a nightmare of a diagnostician, but it can happen in the industry sometimes. It would be interesting to know how a digital tool or an AI tool would be handling this kind of a situation. So now I come to the last part of my talk, where we will be trying to see the human expertise at play vis-a-vis what the digital counterpart would do in the kind of situations that I just explained with respect to asset management and asset fault diagnosis in the actual real life situation. So basically 2 points I will touch upon. One is how the human expert is placed with respect to the capability of AI tools, and can we have a combination, or are they really mutually exclusive? Can we still marry traditional with the smart or the emerging approach to asset management, or they are totally two different kind of situation? It's like water and oil, you can't mix. So let us see how it goes. Let us talk about natural humans versus artificial intelligence. On the left hand side, there is no theory here. It is purely my understanding of the situation and my opinion in this case. You won't find this in any literature. You may not even agree with what I have conveyed here, but this is what I see today. What does a human expert possess? The human expert is supposed to have rich domain knowledge. Of course, he would be typically 30, 40 years of experience in a given situation, given line of business or practice. He would be having his wisdom and experience. He will be having a lot of experiential learning, which he has learned on the job, which may not be taught in a classroom. And human experts are, of course, scarce. They are very expensive. We know, all of us who have tried to hire consultants for advice, we know that how expensive they are. Experts are really scarce and expensive, and that is one thing that the industry had been looking at digital solutions or automated solutions, where some of the functions of the experts can be performed by the automated tools. But experts can be prone to errors. After all, they are humans, and they are also they have the risk of having subjective bias. I am tempted to look at a problem in a particular way, which my colleague may not be doing that way. I may have become opinionated after having spent 30, 40 years in the industry, and a fresher coming to the industry may not look at that problem in the same particular way. I mean, either way, it is good or bad. I don't know who is right or who is wrong, what is better or what is worse. But the thing is that the humans tend to become opinionated, and they tend to attempt a particular problem solving in a particular way after some time. And we humans can be, of course, judgmental, and we can be open to influences, of course. So that shows that, of course, we have the benefit of experience, the learning, the academic training, the domain knowledge, and all that. But we may fail because of certain characteristics of humans themselves. On the flip side of it, if you look at the AI based tools or the so-called AI experts, how would they fare in this kind of situation? They would typically give a very objective output, because all these AI tools are driven by codes which are very structured in a way, and they process data and information in a structured way and give an objective output. The processing will be very structured. Human reasoning can go haywire. You don't follow a particular route when you think deeply into something. Sometimes you will think of one aspect of the problem, the next moment you will be thinking of some other aspect of the problem. We go back and forth, we go roundabout into the circle in a straight line, somehow to find a solution to a problem, try to correlate the data with the knowledge that we have, and try to arrive at a solution. But that is not the same way the AI tool would be, because it is primarily governed by your computer programming. It would try to move in an objective and structured way. These tools are readily available. If you have the money and if a tool is available for the application you have in mind, you can just buy it and apply to your problem. It is easily done. And they are, unlike humans, they are free from biases and influences. Of course, these are computer programs, but they can be expensive. And in this case, of course, we have a commonality with human experts. Both do not come cheap. But you have a requirement, specific requirements, they need validation. Normally, in case of human experts, if he is acknowledged as an expert and he has a standing in the industry, people normally would not ask to validate his judgment or his recommendations. Whereas in case of computer program generated output, you would definitely would like to, particularly if if it calls for a very heavy investment or a very huge capex outgo, the plant owner would definitely like to have a second opinion before following the recommendations. And then you need upgrades and training continuously, because the computer domain is such that every 3 or 4 years you have a generational transformations in the technology, both hardware and software. You have to keep up with that. You have to be up to date. So you have to continuously invest in being up to date with the technology. So it continuously needs upgrades and training of your people or the experts who will be operating those tools. And you need robust hardware and software platform. Again, that has to do with this upgrading of the technology over time. But you have a risk of possible logical and coding error, particularly if the validation or the beta testing of the software has not been performed properly. You have a risk of landing up into wrong judgments and recommendations or diagnostics, which may not solve your problem actually. And it may even lead to larger problems. So that is a risk that you run with the AI based tools. This is basically a way of looking at the mechanism what human experts would be following in diagnosing a problem or doing a troubleshooting or doing an asset management kind of exercise. On the left hand side, I have shown some of the basis or the knowledge elements that we experts will be using. On the right hand side is the kind of tools and techniques that will be applicable in that case. For example, when we are trying to do a troubleshooting, we normally use the if then kind of rules, the consequences based on some causes. And we do that very routinely in a vibration and noise analysis, because you see the spectrum, you see a frequency, you tally it back to the cause, and you say, okay, this is something that is causing the problem. Similarly, of course, I will not be explaining every line here. Similarly, you have the graphical plots and diagrams, as I mentioned in case of journal bearing fault diagnosis. You look at those plots, you try to map it with the nature of perfect or the desirable plots that you have in mind, and you try to see what's wrong in it. You have a statistical model of your system. Probably you can run the statistical analysis to look at the probability distributions and the kind of correlation you establish, and try to derive something out of that. This is typical of the reliability studies, which is primarily based on statistical model. Then of course you have visual inspections, you have image processing patterns like we saw in the case of thermographic images. But the last block, which I have put in a box just to draw your attention, there are certain elements of knowledge which we use routinely as humans, which is very interesting because you cannot really put it in a very structured manner. For example, the prior knowledge or the past experience or examples that we may have seen in our career, that teaches us something, and we use that knowledge in the next time we will be doing similar kind of a diagnosis or an assignment. Similarly, there are a lot of heuristics that we humans follow, which are rules of thumb, which may not have a very solid theoretical basis. And then of course, as I mentioned, experts would be having a long experience, and they learn a lot in the course of their experience, and they effectively apply it in the work that they are doing. And then something else which we popularly call as gut feeling. I feel this is the something, this is the problem that is happening in this pump set, or this is the problem that is ailing this compressor that is running in the plant. But if you ask me why are you saying that, I may not be in a position to really explain mathematically why I am saying that, but I know that could be the problem, because somehow I feel that is to be the problem, because the kind of symptoms or the nature of symptoms or evidences that I am observing from the machine. So this is very common with humans, and in many times it doesn't have an academic or a theoretical basis. But nevertheless, most of the time, lucky for us, most of the time those kind of prognoses are actually correct. Even though we don't know the basis of it, we know the solution, we apply the solution, and it solves the problem most of the time. Now come to the way the AI tool would be functioning in the similar kind of a situation. What would be the knowledge elements that will be feeding the computer tool or the AI tool or the digital solution that you are employing, and how it will be processed by the tool. In the first part, as you can see, the theoretical correlations, the mathematical derivations, signal processing output, graphical plots, all these can be codified and fed to the tool. These are structured data and information you can very easily correlate, and the computer program can be actually trained to process it in a certain way, give you the output. But again, as in the last case, if you look at the 3-4 items at the end, which I have highlighted here: past example, prior knowledge, rules of thumb, heuristics, gut feeling. How would you teach the AI tool about all this? This is so very typical of human. You cannot really codify in a structured manner, develop a computer program, train that program 100 times, 200 times on a case, and then deploy in the industry to solve the problems. This is where the disconnect comes. This is where probably the AI tool may not really be in a position to replace a human expert. This is what we feel today, because we see in the industry, we see today the advent of the digital solutions in a big way. We are into IIoT regime for almost a decade now, and a lot of it have come into the industry and being used routinely. And of course, we humans are still there manning the industry, running the industry, and doing troubleshooting in the industry, and we know how we solve problems. This is one area where probably today's technology is not supporting us in a way the human expert can support the problem. Just to show you the configuration of for example, the diagnostic system, digital diagnosis system, that would look like in the industry. For example, what we are doing as humans, primarily we are going to the machine, collecting a lot of data, processing the data, applying our own domain knowledge on that, arriving at some conclusions, and giving recommendations or advice, right? So these are the same blocks that I have shown here. If you consider this as a digital platform, you will have a lot of sensors mounted on the machine which are collecting the data day in, day out, maybe in real time. You feed the data, you pre-process and analyze through some digital platform. It could be your cloud resources for storage of data, it could be a data historian, it could be a digital tool, a digital model of the plant that is running. You could have some specialized solutions which are based on artificial intelligence and machine learning, and you could have a lot of analytics built into it depending on the volume of data that you generate from the plants. So when all this is done, the domain specialist would look at that and give some recommendations based on the processing that has been done in the previous step. And what could be the output? Like, it could be expert advice, it could be remote diagnosis output, it could be some remedial action suggested to the plant operator, it could be certain kind of recommendations given in the form of an apex dashboard to the top management in the industry for them to take the decision for the future, whether to basically retire that piece of equipment, whether to replace it, whether to go for new capex, or you set up a new plant altogether and basically demobilize or decommission the existing old plant. These are some of the decisions that will be driven by the recommendations given by the expert. So this is kind of a flow chart that basically maps the way we human do the process, and this is how probably the digital platform can work to deliver the same kind of output that human experts are delivering today. Now, if you look at the overall plant-wide implementation of the same scheme, this I showed for a specific piece of equipment. Now, in a plant, you will be having hundreds and thousands of pieces of equipment, and if you then want to map all of them in this kind of a digital platform, this is something that it would look like. At the bottommost layer, you have the hundreds of sensors that you have put. You have instrumented all your pumps and compressors and turbines with this. You have connected all of them to a data collection unit. It is also taking input from various kind of studies that you may be doing offline. For example, as I mentioned, reliability studies, RBI studies, HAZOP studies, failure analysis studies, and these will be all fitted into the uh, uh, database that you are developing with the sensor readings coming in. And then you have a data historian, which is basically maintaining the archive of the historical data that you are generating from the plant over weeks and months and years. And once you do the analytics over all this database, you basically come to the output. It could be a form of digital log. It could be KPI based monitoring. It could be alerts and notifications. It could be a lot of reports or MIS documents. It could be role based dashboard for different layers of management, or the control room operator, for the plant manager, for the maybe the chairman or president of the company. They would like to look at different kind of output from the plant to take their decisions in the day-to-day life. You could get predictive and prescriptive solutions coming out of the data analytics. You could get plant performance analytics, how the plant is doing today compared to last year, how it is expected to do in the next year, and things like that. So this is all happening at the plant level. Maybe if you are connecting the plant facilities through a cloud mechanism, then it is of course remote. You can be anywhere in the world, but you are still able to see your plant in real time. As you see the top block, which is shaded green, which could be happening anywhere in the world through the cloud mechanism. You upload everything from the plant into the cloud. That can be accessed from anywhere in the world where the management team would be sitting, and they will have a real time picture of what is happening in the plant, and they can take decision and guide the people in the plant to operate the plant in a particular way. So here, of course, you see a lot of technologies coming in, both in terms of the sensor, the data processing, the analytics, and the infrastructure or the network that will be carrying all this data. But predominantly, they are giving the same kind of output that would be given by the human experts. Okay. This particular model, by the way, is known as Edge to Enterprise. Edge is what you see at the bottommost layer, which is basically the front end of the machines or the pumps and the compressors and the turbines that you have in the plant. They are typically known as Edge in the today's parlance. And the enterprise is the entire conglomerate of the business that will be running globally in a large organization or a corporation. So this platform basically takes the information from the edge to the enterprise management level. So that is why it is known as a model that is edge to enterprise. And this is one of the most comprehensive model that is being talked about today, implemented to some extent in some of the large industries. I wouldn't say it is yet the state of art, but it is something where we are going in near future. So if you really want to implement this kind of digital asset management solution in your system or in your facility or in your plant, what would be the roadmap? How would you go about doing this? First of all, we have to be really very realistic and objective in what we want to do. You can't have the moon if you want it, but you have to. These are real assets you are dealing with. This is real money you are dealing with, and this is a real-time industrial environment that you are dealing with. So you have to be very practical here. You identify your critical assets. Maybe a small pump with a standby may not be as critical as a turbine having no standby. So you would rather focus on the turbine rather instead of a small pump. Then you have to select the digital solutions and the platform very carefully. There are a lot of suggestions. There are a lot of alternatives available in the industry. Not all of them may suit your particular requirement and your kind of industry. So you have to be very careful in choosing the platform. And we commonly make the mistake of generating thousands and millions of pieces of data, and 80% of that we never use. And it's a big reality in today's industry. We spend a lot of money gathering the data that is never getting used by anybody. And how to optimize the data, how to rationalize and basically streamline the data that is coming from the field is a big challenge the industry is facing today. And you have to start small and grow big. You cannot go to the ultimate, the full model that I showed. It is very difficult for any industry to adapt a full digital model, start to finish, edge to enterprise. You basically start in small step, build up your capabilities and your infrastructure, and gradually go to the top level. That is how it should be. That manages your cash flow and your capex deployment well, that trains your people in a proper way, that brings in the right mixture of human interface with the digital interface so that you can do not cause any upsets in your operating industry, right? And the performance of validation is a very critical step, because we are, as I mentioned, we are dealing with the digital tools and solutions. You are not always sure that 100% of the time they are giving you the correct output, because it all depends on the kind of data, the authentic data or information that you are feeding to the system. That equally applies to the human experts, but it is more so in the digital case, because it is in a black box. You do not have the freedom or the liberty of discussing with the AI tool. It will give you the information based on whatever information you have fed to it. In the case of humans, you can actually have a session with the expert, try to understand his philosophy, his line of thinking and logic or reasoning, and you can counteract that. But you can never do that with a AI tool. So that's a problem. That is why the validation is so much needed in case of a digital tool. The most important thing, as I mentioned in the beginning, is basically to be realistic. Keep your eyes and ears open and feet firmly on the ground. Don't get blown by the digital revolution. There are very real issues to be considered before you can actually select and deploy a digital tool in the area of asset management, because you are dealing with billions of dollars worth of assets in the industry. You cannot just take any irrational decision. Now, let me end this talk with two pieces of thoughts which I have called as food for thought, very different from what I have been talking about so far. Let us take the case of Boeing 737 MAX 8 plane that came into service about 4 years ago. And we had two tragic accidents, very serious accidents. A lot of people lost their lives. It gave Boeing a very bad name in the industry. It has the ultimate level of computerization in the controls. And as I've shown in the quote from a Boeing commander, they typically call it the Mad Max, that is the Max airliner, Dreamliner. It has a mind of its own. The pilots cannot do anything to control it. The accidents happen because of the faulty computer software for the pitch control. It wrongly sensed that the aircraft is going up, and it forces the aircraft to go down, nosedive into the ground or the sea, and that is how the two accidents happen. And once it goes into that mode, that pilot has no physical control to stop it. That is the level of digitalization that had gone into this plane, and not to a very uh, good end. I would say it's a very serious problem to have in hand with this kind of digitalization, though it is very efficient, very optimized, maybe state of art, or even beyond state of art, maybe futuristic, but you have a flip side of it. The other example that I've quoted is a bit in the lighter vein. The Alexa baby that you might have read about in the news a couple of years ago. The newborn baby, when it started speaking, it didn't say mama or dada, which is normally the case. It spoke about Alexa because that is the word that it hears the maximum in the house, in that particular household, because everybody is depending on the digital assistant Alexa to do their day-to-day activities, to manage their day-to-day activities. So that is how the baby learned that word as the first word in its life. So these are two flip sides of the extent of digitalization or dependence on technology that we can have in our life, both in industry, in profession, and in social life. And probably we need to stop here and have a thinking. How do we strike a balance? The kind of power that we have in human brain and wisdom and experience and expertise, how to marry that with the emerging digital technologies that we can't prevent it. Technologies are here to stay. They will grow stronger and stronger. But there is a flip side, as the first example on top shows, that it can be counterproductive for us, for the industry, for the society, for all of us in real life, in the real sense of the term. So, how do you balance it with the right optimistic mix of human and digital, probably technology and the human characteristics and capabilities? So, basically, automation versus human capabilities, pervasive implementation of AI with an appropriate human control built into the process, and digital smartness versus our social and ethical values. See, these are some of the things that we will be thinking more and more in the days to come. All of us will be forced to reflect on these points. And I hope there will be a solution that will be emerging where we conclude collectively that yes, both human capabilities and digital smartness can complement each other. There is a good productive correlation that exists between the two, and they are by no means mutually exclusive. That means either this stage or that stage, because we cannot avoid either of them in our life. We need the humans and we also need technology. So that is how it should be. That is how I look at it. Probably that is how hopefully it is going to emerge in days and years to come. Let's hope so. So with that note, I would like to conclude my talk, and thank you very much for your patient hearing. I really enjoyed speaking to you about some of my thoughts that I've gathered over the years in the industry. You may agree with it, you may not agree with it, but that is what it is. And I hope it will give you some more food for thought for you to reflect upon and try to use some of these pointers in your day-to-day life. Thank you so much.
My sincere thanks to Dr. Varun Chakravurti for his very enlightening lecture for our students as well as all the audience here. So we can have some questions from the audience. So Dr. Bidyut Pal, how much time we can have maximum for this question and answer session?
No, sir, we don't have any set deadline, so as long as we can continue.
Okay. Okay, so from the audience, we can start one by one. If you have any question, please put
Yes,
the question. I
yes, I
think
have
one by
unmuted
one we can.
everyone.
Can I speak something, please? It's not really a question. Am
Yes,
I
please.
audible? Yes.
Yes,
Sir,
sir.
we
Yes,
can hear you.
yes, yes.
Right. So I enjoyed Dr. Barun Chakrabarti's lecture. It's some of them are really beyond my knowledge base, beyond my concept. I'm an old man, graduated in
So am I.
1961.
Yeah. Today, yeah.
But I was thinking the last stage of his lecture, AI versus human, that was rather interesting. Some of the things are coming to my mind, and that is, you see, when you are going to use the AI never gives you the answer in plain English unless you program it to do it. So what you have to do, you cannot use an AI data at the when you need, say something has gone wrong after 3 4 years, 10 years of service, then you start using AI. That will be extremely difficult. You have to, as Dr. Chakrabarti has said, you you have to validate the equipment. That means if you have to use AI in place of a human expertise, you have to use the AI from the day one. You have to know what are the responses when the machine is running fully 100% efficiently, and gradually how the data is changing. And then you need a human person to explain or read the responses given by AI. So ultimately, even if it is AI, I don't know at what level of automation the AI will tell you exactly what is wrong. I cannot imagine that level of automation. So I feel it will give you, if you use it from the beginning and if you validate it, then it will give you some data, and some human expert has to read it and find out the fault or take out the fault from that. So that way we cannot do away with a human expert. And cost-wise, installing an AI from the beginning and running it, and the cost of maintenance. Somebody else who is expert in AI, he or that company will be maintaining the system. So that cost comes something very critical. So with this, I just am stopping, and I have given a little bit piece of my mind. That's all. But I have listened to the lecture, and at my age, whatever is to be learned, I have learned quite a lot, and it was very structured lecture, beautifully presented. And I thank Dr. Chakrabarti for this delivery to all of us. Thank you.
Yeah, thank
Same
you
with
very
me,
much. And
Achyuta.
yeah.
I also found the lecture to be outstanding lecture, and I have requested the department to invite Dr. Chakravarti for a series of lectures for our students and the teachers of design courses. It will make them real engineers, and they will find it extremely beneficial when they go to the industry, even for their interviews and so on. But here, on the other hand, as taking the cue from Achyuta and Dr. Chakravarti, the latest example of using this kind of expert system, because AI term, though we use it, but it has been now found that it is not been possible to find out what exactly is intelligence, because human being, they have something which the largest computer has not been able to show, that it is intuition.
Exactly.
And therefore, the presence of human being will be always essential and necessary. The latest thing, what I have come to know from United States, that now meeting a doctor has become so difficult. If you try to get an appointment, it will take months to get it. So what Amazon is thinking to develop an expert system, which I think 90% part of the doctor's work is the diagnosis through a set of question answer and checking the data and parameters. So that they will get done without having a personal meeting. And then in 90% cases, they find that it will be not necessary to have a personal meeting, and the doctor can prescribe the medicine or the treatment, so that people don't have to wait for months to have actually a meeting with the doctor. So this is going to be again the same thing like your gearbox. Human body is an extremely complicated gearbox, and I think these concepts are becoming very interesting, and its application can be in all kinds of things, as I've just mentioned, even the treatment of human beings without making a physical presence and meeting the doctor, which is so difficult nowadays. So thank you, Dr. Chakrabarti. I enjoyed
My pleasure.
this
Thank you so
lecture.
much.
And as Achyuta has said, it is extremely structured. I am teaching for 57 years. So I understand when a lecture is truly outstanding and excellent. So I must
Thank you,
clap
really.
my hands, being a very old teacher, that you have done an excellent job. And please help
Thank
the
you.
department in
Yeah,
that today we also
definitely
learned.
do.
So we also learned a new phrase today. We noted natural human. In one of his slides, there was this term, natural human.
Yeah.
I was just thinking it's because of this AI and might be due to robotics, we needed this additional adjective for human, natural human.
Yeah.
Good. Indeed, it's very nice. I mean, it's unusual area that he has covered, but very nice, so nicely, excellently covered.
Thank you.
We have a couple of comments, including one that Sir was mentioning. Chairman might give opportunity to that audience.
So may I ask some questions? So one question. I'm
Yeah,
Shantanu
please,
Das
please.
from a faculty member from Department of Mechanical Engineering, IIST
Yeah,
Shibpur.
and from design side.
Yes. So basically, when we are feeding this AI thing in the diagnosing gear failures, so whether we are including the equation of motions or only we are using the data comparisons.
See, basically, what we do is it is not the mathematical basis is not fed at all. What you collect is the sensor data, which is done, which is processed through the FFT analyzer, where the frequencies are filtered out, and you instead of the time waveform, you get the digitized data. And basically, it's a mapping done by the software program, where the characteristic frequencies which are possible in that system. For example, I showed a set of gear frequencies, a set of bearing frequencies. Maybe in a rotating equipment, you will have up to the 10th or 15th harmony of the rotating RPM signal. And it just scans the filtered spectrum to have these matches of frequencies. And whatever frequencies match, it picks up that fault as if and shows it as a probable fault. Yeah, there is no mathematical basis fed to the typical diagnostic programs that we have in the industry today. I wouldn't say all of them are very matured or very complex programs. These are basically if then kind of rules. So they do the matching of frequency, phase, and the time pattern of the trend, and then just give some recommendations at the first level. But there are research going on, there is research work going on, and also the attempt to have some kind of neural network, which became very prevalent in research in maybe the late 80s, early 90s, which has not yet come to that extent into the actual industry today. We have not seen any neural solution coming to the diagnostics application yet, but the not the structured coding and frequency mapping, but you just feed the raw data and let the program find out the way it should diagnose the input that is coming in. There is a big challenge in the validation of this kind of output. So that is why it has probably not progressed to the extent it should have. But that is something people are thinking about. For example, when you give a problem to the human expert, you don't tell him what way to look at the data and how to process it. It comes automatically based on the experience and the expertise. And the same way, the tool, whether it is expert system or AI tool, whatever you're calling it, I personally feel expert system is a better connotation because it brings in the element of expertise. But the popular jargon today is AI tool. Basically, you don't tell the tool what it should do. It should decide based on the nature of data and the nature of system that it's tracking, and decide on the course of action for processing the data and giving the output.
Yes, unless there is no equation, so that means humans being already have decided that find out through equations or something else that these are
Because
the
if
failure.
you see, if you see in a gearbox, we know if there is a mesh problem, the dominant
Yes,
frequency
yes.
will come at gear mesh frequency. So you don't have to again derive the equation of motion and the force balance and then find that the response will come with the frequency of excitation, which in this case is a mesh. And so you don't have to do that because it is already known and proven.
Yes,
It's filtered knowledge, you can say.
yes, yes. Okay, thank you, sir.
Students, do you have any question? Please, you can go ahead.
Put up my points.
Mhm.
May I put up my points, please?
Yeah, please
Yes,
go ahead.
yes, please, sir.
Okay, I am fortunate that this is the first time that my computer has permitted me to enter this WebEx program, and that is the reason that this is the first time that I am joining this series of centenary lectures. I thank the host and Dr. Varun Chakravurti for this wonderful lecture.
Thank you. My pleasure.
It, I feel, is very nice for ground level career engineers like me who have worked in industry and not in the software profession. So today, mechanical engineers graduating and then joining IT industry may not find much use, but it is good for the industry as a whole and for us career engineers. My point is, in fact, I have already shared my thoughts in the question and answer.
Yes.
That is, unlike for civil engineers in institutes who are called upon to investigate causes of failures of bridges and structures, it is very remote that mechanical engineers from industry are being called upon to probe into breakdowns in industry, power plants, or accidents in railway or on traffic. This is very infrequent that institute educationists are being called upon. That is unfortunate. But I feel, as Dr. Chakrabarti says, that there are plenty of diagnostic instruments and tools which can be used by educationists, the academics in the institute, in the industry to help them, because the full range of instruments or tools may not always be available to the industry, and they will be available with the institute, and it is an opportunity for the professors, the to take this up in cooperation with the industry, to have the analysis, to have the research, to recommend the way and the control system for the remedial measures. That is a very good opportunity, and that is the reason that I parameters of professors in guiding PhD qualities. It should be enthusiastic for all educationists in engineering institutes to have such projects in collaboration with industries for the and all these reports or tasks that they perform in industry.
So these are the things that I had thought that I should share. One is that why should mechanical engineers or even for analytical things in the everyday life, and then the investigative approach, and then the performance yardstick. Thank you very much.
Thank you.
Well, if I am permitted, Dr. Chakrabarti, I can take one example where it was a terrible thing. All the industry stopped, and I was called. I'll tell you a story in 2-3 minutes. It was McNally Magor. It was some time back.
Yeah.
Their order position was such that they are offering gear delivery of 2 years at that time. Steel, Bokaro, and all these plants were being made. Now, they made a new plant besides their existing factory, which the structure was a portal, and they had a 10-ton crane. The moment they are starting the crane, the whole structure is vibrating. The union is said, we are not going to enter that structure, the new structure. I was called. I went there and I saw the whole factory stacked up with forged gear blanks, forged shafts, cast covers. There may be hundreds of tons of material lying in the new shed. Not the workshop. The people are not entering that. I said, come on, start the crane. They started, and there was enormous vibration. And since it's a 2-inch portal structure, the whole structure was vibrating. So I thought somehow, I went up, and then I thought, must be the supplied torque in the long travel motor is more than the required torque. Then I found, yes, the motors are 2 10-kilowatt motors for a 10-ton crane at the 2 ends and connected by a shaft. That was for the long travel. So what I did, just changed the delta connection to star, and then told them to start. It started rather slowly, but no vibration was there. It was a beautiful solution. So all the people in the workshop and everybody was very happy, and they started, we can start our workshop tomorrow. So this kind of thing is human expertise is needed. It is rather very difficult to this kind of thing with the AI diagnosis.
Yeah, that's a beautiful example of gut feeling. You felt that, of course, I would be keen to understand how a digital tool would interpret that problem and solve it. Probably it would not be able to.
Thank you.
Good evening, myself, Dr. T.K. Singho. I worked in Indian Ordnance Factories. Indian Ordnance Factory is 220 years old, but it has still started implementing AI because it has a lot of advantages. So I little differ with Achyuta that it has to be started in the beginning. That is not actually not correct. Okay, even if you are old, you can start, and in course of time you will get the advantage, and more you become older, after implementation you will get better results. That is the probably it is correct. And for artificial intelligence, if we use almost 95% problem will be solved, you will be able to detect the problem. Only 5% or something even less than that, where you will not be able to. And there is a expert will play. That is according to my opinion. Lecture was fantastic with the fluent flow.
Thank you.
This shows how much rich knowledge and experience you are having. Thank you, Chakrabarti.
Thank you so much. Thank you. I just add a comment to what you said. In fact, the current approach that we adopt in industry is that most of the plants, particularly in India, are brownfield plants. They have been operating for 10, 15, 20 years. And if they have to adopt this kind of digital tools, what is being done is basically you do a baseline study of the health of the equipment today, because the AI tool would not have the liberty of going through the operating history of 20 years or 15 years that the asset has seen. So you do the baseline study. Output of the baseline study is fed in the the data integrator, which is the front end, and the AI has the advantage of knowing today where the design or the health of the instrument equipment stands, and based on that it does the diagnosis. So it doesn't have the benefit of 10 years or 15 years of operation. But very critical point here is the baseline study, what you should capture and what you cannot, or what you should not capture. It is not yet perfect. This is just an approach today, that you do a baseline study of the equipment that you want to cover, feed that as the input to the automated tool, and try to see how best it can. But as you know, with all artificial intelligence gadgets or programs, the key is in training the tool. You train the tool with 100 and 200, 300 kind of past cases, so that it recognizes the pattern of diagnosis, the line of thinking, and in subsequent stages apply the same line of thinking in the similar type of data to give you the diagnosis. If the training of the tool is not perfect, or you have trained the tool with cases which are not really similar kind of cases in that industry, then of course the diagnosis will have no meaning. So that's a big challenge in training of these tools, and proving these tools, as I mentioned in the talk, the validation of the output from the tool.
Great.
Partho, in the end, give me a minute.
Okay, last I think 1 or 2 questions from students. Any students are interested to ask any question? They may be waiting. That's why I want to see anybody wants to ask anything, because this opportunity may be rare. This industry perspective is the thing we miss it in regular classes. So this is an important aspect what we have seen today. So any student want to ask any question?
And that's why Professor Ghosh suggested that we get him again on
Definitely.
other forum for interaction with students.
That
We'll
I
try to
agree
make-
wholeheartedly. I agree wholeheartedly. He's a brilliant, knowledgeable human being.
He has also
Dr.
given a
Chakrabarti,
lecture in 2016. Ochuda, he has given a lecture. Dr. Varun Chakravurti, do you remember 2016?
Yes.
I think, in the area of the
Tribology
biology, he has
program,
given
2016.
a-
Yeah.
It was a great
Yeah, I
lecture
remember.
from that.
Tribology.
Everybody enjoyed.
Uh,
For the information for Achyuta. Okay.
Thank you, bhai.
So
Thank you,
Dr.
Shantanu.
Chakrabarti is an excellent lecture he has given. And that also repeated these 2 days also lectures. That day also recorded that person. Okay.
We'll surely get him. We'll
Yeah,
surely
it will
get
be
him.
my pleasure.
I think
I'll be
he is
very
also
happy. Just
topper.
let me know.
Partho, you should
Yeah.
remember Dr. Chakrabarti is also topper in 1986. He's a
Okay.
topper. Okay, that should be mentioned in your.
So I sorry to miss that. So that is an
Okay,
important
he's a
point.
topper.
We also miss that.
Okay.
Yeah. Anyway, I think let me take this opportunity to thank our today's speaker, Dr. Barun Chakrabarti. It was really nice to hear you out here. I must also thank other members of our alumni, the senior members in particular. We are getting Achyuta almost on every day, every Tuesday. We are getting Professor Ghosh. We usually also get Professor Mullik and others also. Even our alumni, members of alumni from US, they are also joining many of the times. So it's really, I mean, this forum is working well. Thank you, Dr. Chakrabarti. I must also thank.
My pleasure. Thank you so much for giving this opportunity.
We are enriched. I must also thank today's chair, Partho, my friend, also my batchmate, you can say. So for hosting this session nicely.
Please don't mention here. I think it's I think
people to interact nicely.
Honored much.
Thank you very much. And I would also request you to virtually hand over a certificate of appreciation to Dr. Chakrabarti. We are supposed to send the hard copy along with the memento sometime later. So this is what we can show here online.
Yeah, okay. Thank you. That's so kind of you. Thank you so much.
Mainly, we can offer our love, affection, and respect, sir. So this is the thing for our students. Yeah. I think is a beautiful aspect we can see from the outside world. So this thing, I think they rarely get it. So this is a very rare opportunity. All these things. Thank you, sir.
Very
Thank you.
nice.
Thank you so much.
So it's over, Chair.
Thank you.
For me, the session is over.
Okay, then we can.
Okay. Thank
Yeah,
you. So
thank
I'm
you.
logging
We
out.
can
Okay.
proceed.
Stay
Thank
safe.
you. Thank you
Goodbye.
again.
See you everybody next Wednesday, same time.
Thank you. Bye.